Good morning everyone, this is Praveen from AADS department and my teammates are Kavin Bharati and Siddhartha Devan also from AADS department and John from IT department. We are working on AI-enabled noise reduction in aircraft communication systems which comes under a defined sector, and we are guided by Dr. Anthony Sabapi, assistant professor of AADS department. We found the presence of noise in the audio signals that is being transmitted from the cockpit of an aircraft to the air traffic control towers. These noises were majorly caused due to the heavy noisy environments, and also due to the noises from the engine. People from the aircraft communication towers receives the noisy audio. They find it difficult sometimes to interpret what is being said by the pilot, which can be crucial, and can impact around thousands of lives. For now there are minor inconveniences that is being caused due to the noise, but this problem has a huge potential which involves thousands of lives. We thought of taking this problem and giving a solution. Initially we started on looking to aircraft communication audio signals that were available online. Sadly we did not find any open source audio signals that were available online. So luckily we found out a site that live streams major air traffic control towers audio real time. We used that site and recorded around 20 major channels for around an hour or 90 minutes, and we got the X data there. So for curating the Y data, we gave that audio into a online AI denoising software that uses both mathematical and AI model to denoise audios, which is very computationally costly and inefficient, but it gave good results. So there we got an Y data, and to pre-process it, we trimmed those 90 minutes audio into 10-second clips for the both noised and denoised audio. And like here you can see the visual representation of a noised and denoised audio. The blue represent the noised audio and the red one represent the denoised audio signals. So we did the visualization of Fourier transformation of the audio signals to get an idea which frequency is getting reduced. We also know that computing time series data will require high computational power. Those high computational calculations cannot be done real time, which our project aims to do. So we thought of going with the convolution model. So what we basically did is converted every 10-second clip into Mel spectrogram images, so that we could feed the Mel spectrogram images into our model and convolute it and get the denoised output.
Hi all, this is Siddharth, and as Praveen had explained, we converted the audio clippings into Mel spectrograms using short-term Fourier transforms, and we had planned to use convolution-based autoencoders initially. So what we did was we trained different convolution-based autoencoder architectures. In fact, three. So here are the architectures, and one out of three, one had three upsampling and three downsampling layers, and the other two had two to each. So here is the plot for the three-layered one. The first layer had 32, the next with 64, and the third one with 128 kernels, and the vice versa for the upsampling layers. And then at the end we used a cropping layer too in order to maintain the shape for 313 to 513. That is because we used a hop length of 512 for 16K data with 10 seconds. So calculatively it gives us 513 time clippings. I mean for 512 data width, it gives us some 513 10 seconds will be divided into 513 data frames. So here is the two-layered one with two 64 and 128 kernels, and the vice versa. And here also we have used the cropping 2D layer at the end. And this is another two-layer network with 32 and 64 kernels each. So these are the three convolution-based autoencoders that we have used. And here is the code for that and the loss too. So you can find the loss going down for the second one, which is two-layer and two-layer architecture. Here you can find the summary and the model's code. This is how it is run. We've used SNR loss as the loss function for autoencoders. I mean this convolution based autoencoders. Then that is SNR is a loss function that is abbreviated as signal to noise ratio, and that is a custom loss function that we've written on our own. Because though MSE and MAE can be used for autoencoders, for this particular denoising task, signal to noise ratio is a better loss function, which we found from research papers. So we thought using signal to noise ratio for updating the weights would be a better one, and it seemed to be working better. And also we've also used MSE and MAE as metrics so that we can get the plots of them too. We've attached the plots of MSE, MA and signal to noise ratio loss in our project report, and you can see them here too for this particular model. And later after trying autoencoders, we thought of what if we could exploit the time information that is present in the MEL spectrograms itself. So we thought of using LSTM based autoencoder architectures. That is because though we convert time domain into frequency domain using Fourier transforms, here since we use 512 as hop length and we do kind of a time framed Fourier transforms for 10 seconds, we get 513 time based frequency transforms. So it's for 513 windows of frequencies. So we still have some time information left here. And what we thought was, from the results, we kind of inferred that the time information, I mean the temporal information, is not extracted properly using convolution based architectures. So we thought of using LSTMs on images. I mean the spectrograms, which are basically images. So we used one LSTM based architecture with 3 LSTM layers with 256, 128 and 64 layers each, and the vice versa for the decoder side. So that gave us the following results. You can find them here in the results page. We only mentioned MA and MSC in the results table and not the SNR loss. And later we thought of this LSTM didn't work well actually. Not what we expected was resulted. So what we thought was, what if we combine both of them? I mean extract the features using convolution and then extract the temporal information using LSTM. So we built our own basically architecture using both convolutions and LSTM. So here we used convolution layers to extract the features, and then an LSTM layer with 64 units with inside the bottleneck. So basically encoder and decoder will be of convolution, and in between there will be, inside the latent space, there will be an LSTM. So this gave us the following results, and here you can find the simple LSTM's architecture here. This is it, and the convolution based LSTM, that is the combined hybrid architecture here. The highlighted one is the LSTM inside the latent space, I mean in between the encoder and decoder. Here we have two convolutions like this. So this is the results that we got for LSTMs. And coming to the final results, actually the normal convolution based simple autoencoders seem to work well. That is the layer 2 with the model 2 with 2 layer actually seems to work well with MA of 0.36 and MSE of 5.47, and you can find its results here. This is the second one. So the loss that gets reduced, and here is the MA and MSE. So these are the results for the best architecture that we were able to build. So on total, we've built 5 different architectures basically with using 3 different strategies. 3 are convolution autoencoders, and 1 is LSTM based autoencoder, and another is a hybrid architecture. So for us, the conventional convolution autoencoder seems to give better results for our 300 odd data samples with 2 layers each. So that's all for us. And coming to the future scope of this, we are trying to implement it in near real time. Of course, exact real time won't be possible with this much of processing, with this much computation, but still near real time performance can be achieved by using lightweight models. So and that is the reason for going to convolution based autoencoders and not sequentially processing them using normal LSTMs, because of course we are going to have 16 kilohertz, I mean 16k frequency for 16k as sampling rate, and for 1 second we'll be having 16,000 data points, and sequentially processing them is almost impossible when we expect near real-time performance. So that is the reason we went for transforming them into MEL spectrograms and then processing them using convolutions. So apart from this, if we try to collect even more data, like 1000 or 1500 odd samples, then we can give better performance on paper. So we'll also try play the audio now. That is the one that is noisy and the one denoised by the model. So this is the noisy one.
Tower, South African. The sighting will be ready.
Hello, 519, 103014, Gus 22, runway 31 kilo echo cleared for takeoff.
Clear for takeoff, Kilo Oscar.
And this, the output here is the one that is played, I mean, given by the model.
Tower, South African. The sighting will be ready.
Hello, 519, 103014, Gus 22, runway 31 kilo echo cleared for takeoff.
Clear for takeoff, Kilo Oscar.
So you can find it here. Thank you, one and all.